And then I will characterize the properties of the extracted core population and discuss also the evolution of this extracted population. And finally, we'll give a brief summary of the main results. So as an introduction to the IMA star formation, first of all, an important note that we have to address, to make, is the fact that actually why we are so interested in studying IMAS stars formation and related regions. The main reason is because the majority of the stars form within clusters, including our sun, which typically include at least one IMAS star. So basically, studying the properties of these IMAS star forming regions provides us crucial information on the mechanism of star formation, and ultimately it sheds light on the birth, of stars and ultimately on planetary systems. But we have to be aware of the fact that to study star formation is not enough to go to study single structures at single scales with single, let's say, observations. But massive star formation is really a multi-scale problem. So we have to address the different spatial scales that are in play in the star formation process. So we go basically from molecular clouds, so wide regions of even a few tenths of parsec size. Then molecular clouds host gas and dust condensation, which are called clumps of about a parsec scale. We will see also more details about the structure shortly. And if we observe also the clumps with an higher sensitivity and resolution, we are also able to see that these clumps are actually also fragmented into typically multiple compact substructures on the scales of about a few thousand AU, which are called cores and which are actually the very sites hosting the formation of stars and protostars. Observationally, probably the most suitable tracer to study this, let's say, hierarchic structuring of the molecular cloud, and especially to go from clumps to core scales, is the dust continuum emission, typically at millimeter and sub-millimeter frequencies. And this is what was done and is being done by the two main programs that were developed here in this group in the past years. So that I report here, for example, IGAL, which performed a survey of the galactic plane to extract a catalog of hundreds of thousands of clumps in the far infrared, and ALMAGAL, that I will present today, which is the current program, which with a higher sensitivity and especially resolution, when it was able to go to reveal the fragmentation of the clumps and to study the force basically at a few thousand AU scales. So here I report in more detail some specifications, some properties of the structures involved in the dense scales that we are interested in with ALMAGAL. So the clumps, as I was anticipating, are dense gas and dust envelopes within the molecular clouds, which host in turn the compact cores, which are the actual sites of star formation. I report here some typical values, range of values for the density, for example, for the temperature, typically a few tenths of kelvins, for the mass between typically hundreds or thousands of solar masses, and the typical size, which is of the order of 1 parsec. Regarding the cores, instead, we reach, of course, more higher densities that can reach up to 10 to the 9 per centimeters cubic, and also we can reach higher temperature, up to 100 kelvins, and even more in more, let's say, extreme local conditions. And the typical scales are of a few thousands AU. So the process that brings basically from the clump fragmentation into the cores, we see in the lower plot another example of a clump within the torus giant molecular cloud. And basically, as a very simple approximation, these clumps go through a dynamical fragmentation process in what we can approximate as a gravitational collapse. Of course, this is a simple approximation since we actually know that other effects and processes and forces can have an influence on the process, also mainly depending from the local conditions. For example, also magnetic fields, turbulence effects, and feedback effects between the various scales. So this is a simple approximation. But basically, the clumps can fragment into a wide variety of fragments, compact fragments of smaller scales. And we can see here a sketch of some example Almagal maps where I want mostly to highlight the different morphologies that we observe in our clamp images. So we observe clamps with more isolated and bright compact sources, which can be more easily identified as potential cores. But we also observe clamps with more extended and complex emission pattern, and also structures which seem to be somewhat aligned in filamentary-like structures. We will see more example of that in the next slides. So here are the main questions that I want to discuss about, that we want to address with Almagal and with my work in particular. So for example, I also report here some references about recent papers that address these different problems. So for example, one of the main questions is which are the degree of fragmentation of the clamps, and which are the typical spatial scales of this process, how the compact fragments that are formed are distributed in terms of mass and size, and how these properties are related to the properties of the clamps that host them. Then we also know how the cores do gain their mass and how this process goes with the evolution. And ultimately, we want to see or to understand which are the parameters and forces that drive and dominate the fragmentation process, for example, density, gravity, or turbulence effect. Trying to address and to solve somewhat these questions can help us comparing and let's say shed light also on the more debated mass transformation models that were recently or less recently proposed. For example, about hierarchical fragmentation, which basically describes the multi-scale framework of star formation. So how the fragmentation and the massive star formation goes from one spatial space to the other in a, let's say, a more dynamical and multi-scale framework. And the two main models about massive star formation that were debated in the past years. The two main examples are the core-fed accretion model and the clamp-fed accretion model, even if we have to say that in the past years, basically, most of the research works provided hints towards a more likely clamp-fed accretion in all its possible declinations. Of course, this is mostly a family of models. And I report here just a small sketch to understand the main difference between these two models. The clamp-fed models is more depicts basically that cores, so compact cores, are formed as small seeds and then gain mass from basically the interclamp medium, so from the material taken from the parental cloud, and then go in a competitive way to form a single two systems, while the core-fed model predicts the existence of basically massive cores, which are already there in terms of material present, and that basically collapse to form a single system. So it's more simple in this sense. Of course, addressing all these kind of questions about star formation requires an extensive analysis and amount of data. And of course, to go through all these problems and reveal the most compact substructure, high sensitivity and resolution data are really needed in order to identify the most compact cores and to be able to estimate the various parameters that compose this multi-parametric analysis that is required to have information on the larger framework of the star formation, the massive star formation.
So
yeah.
Can you try to remove the part? Sorry.
See.
Mouse is working. Click on OK there.
Yeah, I have to find that.
Otherwise, never mind. Online, they don't see that, but it's for us.
Yeah, I know.
Now we have to exit the presentation and then we come back again.
Never mind then.
I think so. I'll try very quickly. I can try. Okay, now it's even worse. Okay. I'm sorry, I will pause a bit. Okay. so now I will describe the Almagal project and its specifications. So how basically Almagal has taken the challenge to take on all these questions in massive star formation. So Almagal, why is not going now? Okay. Yeah, but I think I'm sharing, right?
Yeah.
Okay. So Almagal is a large program performed with the ALMA radio interferometer in Chile. The main feature is that it features a very wide range sample of massive dense clamps, more than 1,000 that were selected from the IGAL and RMS surveys. We feature very wide ranges in terms of physical parameters, for example, in terms of mass, in terms of heliocentric distance, in terms of different galactic locations covered across the Milky Way, in terms of the surface density that is were selected to be at least compatible with diamond star formation, and importantly in terms of evolutionary stages that we basically trace through the L/M evolutionary indicator, so the luminosity over mass ratio of the clamps. And this wide range that we have, more than actually 4 orders of magnitude at least in L/M, basically covers the whole star formation sequence from infrared dark clouds up to H2 regions and even more advanced protostellar phases. Coming to some more technical detail, we observed in ALMA band sit, so at about 1.4 millimeters. We chose 2 different observational setups for, let's say, the near sample, so distance below 4.7 kiloparsecs, and the far sample. So we basically combined the different antennas and baselines of the ALMA interferometer in order to achieve different, actually, angular resolution for the 2 subsamples, as you can see. So basically, we combined the 7-meter antennas plus different baselines configurations of the 12-meter arrays of ALMA. And this is reflected in the lower left plot, where we see the distribution of the angular sizes of the beam, so basically the resolution that we have in the 2 samples. This choice of having 2 different setups is actually justified by combining this information with the distance of the source, because what we obtained is the rightmost plot, where we see that we actually, in terms of physical resolution, so the physical scales that we are actually able to access, which is the what actually interests us. This distribution is actually quite homogeneous, and with a median value of about 1,400 AU as a median resolution, with also some more favorable cases where we reach also higher, better resolutions. The importance of this is that, of course, even if we have a very wide range of distances and physical parameters from our clamps, we are able to do a consistent analysis for the whole sample despite its variety. So that's the main rationale behind this choice of the observational setup. We can see a demonstration of this with so the importance basically of the resolution in this kind of study. So we start from the 7-meter only antennas of ALMA, which basically resolve only the clamp scale structure, so about reaching about 5 arcseconds resolution. By adding, in this case, the C2, which is, let's say, an intermediate baseline configuration of the ALMA main array, we start to reveal, let's say, a medium or small scale structure, so a bit of fragmentation within the clamp, but it's when we add also the more extended baselines that we reach the full resolution of our setup, and we are actually able to reveal an higher fragmentation degree, and ultimately we can go to study the compact cores and try to measure their main physical parameters. So this is slightly just to put in context Almagal with the other recent interferometric surveys. So we spoke about some of these specifications. So, for example, in terms of coverage of the L/M indicator, Almagal is expanding the field, the sample available. Also in terms of spatial resolution, which is basically 1,000 AU, so the best of among the recent surveys. Also in terms in the left plot, we see also the number of cores, which I will present shortly. So basically, the statistics that we have on the compact structures that we extract. Also, we are basically expanding by at least one order of magnitude all the other recent surveys about AMA-forming regions with interferometers. Of course, all these kind of data observations required an international effort to collect the data, to process the data, and to produce maps, and then start doing the first scientific analysis to try to take to the best way possible the advantage of having basically an unprecedented level of accuracy and statistical significance of our sample for this kind of studies. So coming now to the more scientific and technical part of my talk, I will briefly explain the procedure that we developed for the compact source extraction. So basically to extract and to identify the compact cores within the clamps to study their properties. So the main problem that we had to face from the start was that, as I was anticipating before, we have a very wide, large diversity in terms of morphology and of emission patterns in our wide sample. So we have, for example, cases in which we have only isolated blobs of emission, which are more easily identifiable, they are also more, they stand out with respect to the rest of the maps and to the noise of the maps. We have also more complex cases which show both diffuse emission and compact sources lying on them and so on. We have also filamentary like structure like in the third case, and we also have very crowded fields with complex structuring and compact emission that we have to disentangle. So the main aim for us to develop an effective source extraction procedure was to be able to efficiently perform in all these different conditions in terms of emission and so on that we have on our maps. So these require the most important effort in this sense. So I will now briefly explain how our source extraction workflow was produced. I will not go into much detail because it's very technical. We can go through it later, but I will also only explain how it works in the main steps, which are basically the detection phase, the photometry phase, and the final filtering of the signal to noise. So for the detection phase, we basically evaluate the compactness of the source. So we select the sources that are compatible with the compact roundish sources using the curvature map, let's say the so-called curvature maps. So basically differentiating the intensity images to to evaluate the intensity gradients over the different directions. So only to basically select only the most compact sources. We test the photometry where we make assumptions actually on the shape of these sources. So we apply a fit on these selected sources with fitting them with 2D elliptical Gaussians, and we also fit them contextually with a background, with a plane, which is aimed at estimating the local background emission to obtain more accurate fluxes, and also because in this kind of maps, the contribution, especially in the more, let's say, complex fields, the contribution from the background emission can be also very relevant in terms of flux. So this has to be estimated and removed from the final fluxes to obtain reliable measurements. So, and finally, we apply signal to noise filtering to select and to obtain a more robust catalog, where we evaluate the background subtracted integrated flux of the sources with respect to the noise that we estimate from the map to do different, let's say, flux cut on our catalog. So this is the outcome of the source extraction, an example outcome of the source extraction procedure. I hope you can see the small photometric ellipses in blue, which are, these are the same clamps as before, but I overlaid the cores that we identified in these clamps. So basically, after a very long effort in optimizing the parameter setups and trying to address all these also technical issues about these maps, so we think that we managed to obtain a quite robust catalog, efficiently performing in all these different conditions. So I can pass now to characterize the properties of these compact cores that we extracted. So, for example, here to start from a more statistical, let's say, description, we have here the distribution of the number of fragments that we revealed across the whole clump sample. We obtained more than 6,300 compact cores in actually 844 clumps, so 83% of the total. The average number of detection per clump is 8. The median value is 5. And most importantly, as you can see in the histogram, we revealed very different degrees of fragmentations, even if with not the same weight, in the sense that most of the sources, most of the clumps revealed one or a few fragments, but we have also a relevant fraction of cases in which we have more crowded regions and also very crowded, up to 50 fragments revealed within one single clump. A note to be made about this is that also a significant fraction of the clumps proved to have no core detection at this scale, so about 70%. But this is probably most probably related to the properties of these clumps. For example, the density and the evolutionary stage, as we will see in part later in this talk, and also is addressed in more detail in the other papers that are accepted or in preparation from the Almagar project. So this is also a note to be done also for this work. So this is the distribution of the core physical sizes that we estimated. So this is the diameters basically, and we revealed mostly sources within 1,000 and 2,000 EU with a median of 1,700 EUs. So this is the distribution of the core diameters. To estimate the masses, one of the key parameters is the choice or the adoption of the temperature, the dust temperature for the cores. In theory, the ideal approach would be to assign to each core to have for each core information of their single temperature, but this requires actually a very deep analysis of the molecular line data, which we have in Almagar and is currently in progress. So we don't have them for now, but it's going to be implemented in this sense. For this work, we chose to base on a model developed by Molinari in 2016, which basically calibrated the temperature, the dust temperature of the clumps by using a calibrator from the molecular species, the CH3C2H. So basically, based on the emission of this molecular line as a function of the allogram, they assigned somewhat a model for the temperature to assign to the whole clump. So we, based on this model, also this was also done by some other recent, some kind of these models, other recent works like Traficante 2023. So we basically assigned to each core the same temperature within a certain clump, based on the allogram evolutionary stage of the clump. So we assigned basically 20 kelvins to the cores pertaining to the clumps with allogram below 1, so the less evolved ones, 35K for the intermediate, let's say, sources, and the temperature proportional to to a power of the allogram for the more evolved sources. These values come from basically a fit of the points featured in the model by Molinari in 2016. And we see a representation of this output model basically that we used in the lower plot. So the temperature range we obtained for the cores ultimately was between 20 and 81 kelvins, which is consistent with most of the estimations and values that are commonly used at core scales, also by the other studies. With this temperature model, we estimated the masses, and we see above the distribution of masses, so basically the core mass function of our cores. We see that we reveal more than 4 orders of magnitudes of mass for the cores, so basically from 10 to the minus 2 or even lower up to more than 300 solar masses. The median value that we have for the distribution is 0.4 and the mean is 1.5. And here I also report the average mass completeness value, which characterizes our sample, which is of about 0.2 solar masses, which we estimated through a flux completeness analysis using synthetic compact sources that we injected on Almagal fields, and basically we injected different flux levels and evaluated at which flux level we were able to recover at least 9% of the sources. So we converted this basically flux value to mass, adopting an intermediate value for the distance to characterize the whole population on average terms, and we obtained this 0.2 value, which characterizes somewhat our Cornus function in terms of completeness. In terms of mass-related value, mass-related parameters of the cores, we obtained also a wide range of core mass surface densities and molecular volume densities up to 10 to the 9 per centimeters cubic, which actually confirm and are actually quite high values, especially for the IAPS end of these ranges. And this confirms that we are basically indeed tracing the more compact substructures within the cloud. So the more compact structures in this cloud. So we are describing the properties of these structures. So going now to the more physical interpretation of these estimated parameters, an important analysis was to evaluate the evolution of these masses. So basically how the mass function of the cores change with the evolution, assuming the usual L over M indicator as an evolutionary tracer. So basically we subdivided the core sample into the three evolutionary groups that I already explained. So L over M below 1, the intermediate one, and the more evolved ones. And we evaluated how the three core mass function for the core subsamples were related and will stand in this core mass function plot, one with respect to the other. In this plot, you also see colored bands for the three groups, which correspond to the Monte Carlo realizations of core mass function that we produced by randomly varying the temperatures around the reference value for the subgroup. And we did this to try to take into account the influence and the uncertainty brought by the choice of the temperature model for the cores on what we observe actually on the CMR. So we tried to, with this 1,000 realization for each subsample, we tried to see how it would impact the appearance also of the three core mass functions. And what we see, I think quite clearly, is that the three subsamples, the three CMF are clearly shifted one with respect to the other, and this was also beyond the possible uncertainty and brought by the temperature, which are shown by the bands in this sense. So basically, the main result that we got from here is that we see more massive cores in the more evolved clamps. And more generally speaking, this tells us that the core mass function shape for the IMAS is not constant throughout the evolution, but it changes, and in particular, the IMAS gets flatter and flatter with evolution. These results were already suggested by some recent works, but of course we largely expand the analysis in terms of statistics and of also variety of the sample featured, especially in the evolutionary stage, in terms of evolutionary stage. This is, as you can imagine, a quite important result. So we performed a lot of other checks and analysis on this to try to remove the possible bias that can influence it. So besides the Monte Carlo realization for the temperature that I already explained, we also excluded from these samples, the core samples, the sources that were potentially contaminated by free emission, for example, from the presence of H2 regions, which is possible especially in the more evolved clamps. So what we did was basically to compare and to match locally the position of the Almagar cores with the emission, with the radio emission maps from the Cornish and Cornish South radio surveys. And where we found a strong radio emission, we matched with our match cores. We decided to exclude this course, which could bring an overestimation of the fluxes due to the free contribution, and so could bring to an overestimation of the masses. So could, of course, influence and affect the shape of the IMAS and of their core mass function. Moreover, we went to also analyze the possible impact of other biases that intervene in the calculation of masses. For example, the distance, the resolution, and other biases coming from the temperature choice. In terms of distance, as you can see, I basically cut here the distribution above the mass completeness value, which is the purple vertical line. And this basically allows to remove the possible effect due to distance, which intervenes in the change of mass sensitivity that we have through our sample, because we feature a very wide range of distances. So mass depends on distance, and the mass sensitivity as a consequence changes with distance. So cutting above the mass completeness value basically makes the range of possible mass reach for the masses equal for all distances, and so it makes a better comparison between the different clamps and also different distances. In terms of resolution and temperature and other temperature effects, we did these other checks that I show here. So in the first plot, we reduced the sample even more to a sample which had a resolution, spatial resolution between 1000 and 2000 EU, so consistent within a factor 2, to see if some lower resolution cases could bring to higher masses and so modify the tail of the core mass functions. So in the first case, we also see that basically the result is still there, even applying this fitting to the core catalog. In the other cases, in the second case, we applied another temperature model to the cores, taken from the one used by Sadagliani et al. In 2020. So basically, we waived the assumption of giving all the cores within a clamp the same temperature, but we based only on the measured integrated flux of the sources, and we applied to them a single temperature proportional to that. And we also see here that basically the evolutionary shift between the three subgroups is still there. And in the last case, we basically simply removed the temperature from the mass formula, basically, and we see that the shift is still there, even if considering only basically the fluxes and the distance of the sources. So all these kind of analysis and results tell us that we basically we think that we obtained a robust result, which is reliable, also based on our wide statistics of thousands of objects. Basically, the results of the evolutionary trend of the core mass function tells us that there seems to be an increase on average of the core masses with evolution. And we can see some more detail here. For example, in the above plot, I show the trends of the maximum core mass within each clamp in median terms here, and the minimum core mass in blue. This is divided into bins of LOM of the clamps. So we see here that the maximum core mass within the clamps clearly increases on average terms with the evolution, while the minimum core mass is almost steady or even slightly decreasing. So basically, this tells us that the cores, at least the most massive core, grow in mass with evolution, but the population of low mass cores appears to be present at all evolutionary stages. This is also investigated in other detail in the paper of Davide, which is going to be submitted very soon, which address the correlation between the core and clamp properties in a more systematic way. The two main interpretations that can be done of this trend, especially for the blue part, is that we could be observing the same population of low mass fragments, which are essentially unaltered throughout the evolution. So we see them nearly steady throughout the evolutionary stages, or we could be seeing new fragments that form as low mass seeds throughout the evolution, and this seems to go in parallel with the simultaneous core mass growth for the higher mass cores. In the second plot, I tried to see if the core mass growth regards basically only the most massive one that could be, in theory, dominating over the core population of the clamp, or it also involves the other cores within the clamp. So basically, on the y-axis here, I plotted the total mass in cores within a clamp minus the mass of the most massive one. in the x-axis, so as a function of the mass of the most massive cores. And I also color-coded for the LOM evolutionary tracer. We see that there is a clear ascending trend also in this sense. So basically, what we see here is that also the mass of the other cores within a clamp seem to grow in parallel with the mass of the most massive ones. And we also see an hint of an evolutionary, a confirmation of an evolutionary trend with the color coding or with the LOM, even if it's not so clear from here, less than what we saw in the other plots, which were plotted directly against the LOM. So these are the indications that we take from here. Another issue that we can, another method that we can address in more detail is how these two possible results are related. For example, the core mass growth and the possibility of further fragmentation occurring in the clamp. So in this plot, I plotted directly the number of fragments in the clamps as a function of the most massive, the mass of the most massive core in the clamp. The red line is the median value within the of mass, and we see that at least until about 10 solar masses, there is an evidence of an indication of an increasing trend. So at least in this mass range, which is quite large actually, the fragmentation seems to go in parallel with the mass growth. But of course, this is an indication, but we have also an hint of stabilization that we have on the higher mass end. But of course, as we see here, the spread of the points is quite large, and we also have some cases in which we have a low number of fragments and high core masses. So this is not, let's say, so clear and unequivocal, but this is an indication that we can explore more. So, and of course, we have a lower statistics in the higher mass end, so this has to be taken with caution. But this possible increasing trend, the hint that we get from this plot is actually consistent with also some numerical simulation works that are being produced recently, for example, by Annabelle et al. Simulating the collapse of a massive clamp, and also with some preliminary simulation produced in the framework of the Rosetta Stone project, which will be also analyzed and explored in more detail in the next papers of Rosetta Stone. Putting all together, basically, we find that this plot could be interpreted as clues towards a possible clamp-fed scenario for Ramazar formation, and the framework that we can depict from that is that cores seem to form at relatively low masses on average, and then grow in mass with evolution, and the clamp fragmentation process seem to go basically in parallel with this mass growth, at least for the most part of the mass range. More generally speaking, the cores are probably gain their mass mostly from the reservoir available in the interclamp medium, so in the parental clamp, since they show basically parallel growth of mass among the whole, across the whole core population, and this depicts and confirms a possible dynamical and multi-scale framework for the fragmentation and the massive star formation process in the clamps. So I'm going almost to stop here. Just give a very brief summary. So we have a very wide, significant sample of clamps within Almagan, observed at high resolution. We have very high statistics in the extracted compass catalog, where we reveal very wide different fragmentation patterns, and also we characterize a variety of physical parameters, cores and masses, more than 4 orders of magnitude. In terms of the CMF, we find that the most massive cores are found preferentially in more evolved clamps, and that ultimately the shape of the inner end of the core mass function is not constant, but gets flatter with evolution. In terms of relation, let's say, an interplay with the fragmentation of the clamp, as it is also explored in more systematic way in the paper by Davide, we see that the cores grow in mass with evolution, and this basically seem to go in parallel with further new low mass fragments that we find all over the evolutionary sequence. So this basically depicts possible leads toward a clamp-fed scenario. So the very last slide is a quick status of the Almagan papers. So we just basically published last week the first three papers about the survey presentation, the data, pipeline presentation and description, and my paper which I presented today. And this was also published and announced by several press releases, both from national and international institutes, as you might have noticed last week. But there are also a number of other papers addressing the different macro issues and topics of massive star formation, which are either already submitted and currently revision, or will be submitted very soon, or are still in preparation, both about these kind of studies, about more the fragmentation properties and the correlation between core clumps, but also about the more, let's say, chemical part, about using the molecular line data, about also investigating the dynamics between the different states of our clumps, which are the matter of a lot of these papers, and also other that will be produced in the next years. I think I'll stop here, and thank you for your attention. Thank you.
Here, Alessandro. So, thanks for the question. First, I will see if there are questions from public here, and then please from online raise your hand or write in the chat. So, is there any question for Alessandro?
Nobody else.
I see Alessio. For the moment, I don't see any other, so that's good.
So first, thanks, Alessandro. It's a really impressive amount of work, for example, your PhD. So I was wondering, if you can go back to the CMF distribution. No? So we assess now that this core grows with time. So the CMF.
Yeah, the trend.
Yes, so we see some cores which are impressively massive, higher overlap, about 100 solar masses, assuming that the temperature was estimated on the factor you have discussed. So those are possibly, I mean, they must grow from something that is smaller, as we noticed. If you look at yellow overlap less than 1, so the very young object, we have already cores that are above 10 solar masses, probably even 20, which is quite a lot for a young object. So I was wondering, have you ever checked? Since we have a huge spread of LOVM below 1, between 0.05 and 1, so it's one order of magnitude more or less. If the one at 10 to 20 solar masses are the one at LOVM living nearby 1, or they are extremely young objects that already have formed this extremely.
So basically a sub-trend between the sub-clump, further
I'm
sub-deep.
wondering if you can try to check also then the inflow rate of these objects for the next alpha pole, for example. Because to grow that much and still being kind of lower end, that's a very interesting object.
Yeah, I think in the, let's say, yellow subgroup, we reach 15 solar masses, or 15 the most time. There are almost single counts, so that could be also that they are for sure a different object, but it's possible. I think we did it when we were trying to assess the best way to subdivide the sample in evolutionary terms. So we also did some further subdivision between LORM, and of course the statistic gets really lower, especially for the LORM below 1 sample, but there was an hint of that. So of course the very high mass objects are almost single counts or very few counts, so it's not so easy to say about they could be extreme values and so on. And of course we have to remind that these are average clump properties that we assign to the course. So it's not, we cannot exclude that single course can have actually a different properties to what has been estimated at clump value, at clump level on average terms. So actually core will have an internal distribution of temperature and so on with respect to the average clump. So for single cases, this could be also the case. But yeah, I think that we tried some of this, and the trend also between the smaller ranges of LRM was already present. So one could see more detail on also the single objects. If, yeah, could be also more analyzed in detail.
So, any other question? Actually, I have a question and a comment possibly. Let's start with the question. So, there is this typical paradigm in star formation where we think that the IMF and the CMF are related by a fraction, but one of your results here, it seems to showing us that this paradigm is not something that is rigid and following up to the early stages. How much the CMF that we're showing here match what we had from IMF? So which one of those are the ones that are more compatible with the IMF?
Well,
I see different slopes here.
Yeah.
So which one of those is more similar to the?
Well, the issue of evaluating the slopes of the MSN is quite tricky because it depends, of course, on the statistics, but also mostly of the assumption that you make and on the kind of sample that you have. So, of course, we are kind of mixing all different kinds of clumps. So, of course, here we will have effects from single properties, from clumps with different properties, which will mix up in some sense to what you observe as a final core mass function for the Olsa groups in this sense. In terms of IMF, yeah, for sure there is no a rigid shift between the different evolutionary stages. And in terms of slope, we find basically that it goes flatter with evolution. And if we did some estimations, and basically we find that it's, let's say, a bit more with respect, for example, to the Salpeter one, which is the reference one. The lower, the less evolved ones, the slope is less, is a bit more inclined, so it's more steeper, while we get flatter and flatter until reaching much higher values actually with respect to the Salpeter reference one.
So the blue that are the more evolved are more similar to the Salpeter, right? Salpeter is the IMF.
Yeah, it's even flatter, but for sure it's more similar to what we find in the very first stages.
Okay, because, so yeah, for the case of the high mass clump and high mass formation, possibly there is this transition, while in the low mass they generally assume that there is you form a CMF and then you have a
rigid cut. Okay. Yeah, it seems so. Yeah, we basically approach on wide terms, we approach more the expected IMF going with the evolution in this sense.
Okay. And another question is, you show that there is a general not so high number of fragmentation in your system. Where are the clusters? Where are those objects should form clusters?
Yeah.
We know that star clusters are formed by 100 objects. Where are they? I mean, it's just more a comment. This is open a lot of other questions.
Yeah, partly we are, let's say, we cover more the, let's say, the sample was also selected to mostly cover the prestellar phases, although we have a wide range of, in terms of statistics of, in terms of L over M. So basically, there could be that most of these, at least on average, is what we have, that they could be simply mostly younger regions that tend still to fragment more, because basically also the core can form multiple systems in this sense.
So you show that the number of cores grew
on average
L over M, basically with the mass of the most massive, but that grew also with L over M. That tells you that the fragmentation increased with time, and possibly the clusters are fragmenting over a wider time, a larger time than just a single pass. This is what maybe they go.
Yeah, and this could be not simply linear, so fragmentation could, let's say, accelerate with time, and so that if you don't observe really evolved clumps, you have even fewer fragments than what we do expect from a linear growth, for example, of fragments. This could be, of course, the spread also here is quite, we have a number of cases, so it's not so univocal, but this is the most likely explanation in a sense.
Thank you. So any other question? I don't see any, so I think we can thank Alessandro again.